Welcome back everyone. In this lecture we will actually continue with the universal constructions. So now we will see the construction of exterior algebra, which is very much related to the alternating tensors or the exterior products. So again we can actually just define it using the Goic modulo some two-sided ideal generated by some relations. So what we are interested in, actually if we take the product of elements from the capital V, so that should be thought of taking tensor products, okay, just simply taking the products, okay. So tensor product should be thought as taking product of basis elements, okay. So in a more abstract way, so basically we are taking that monomials in the basis elements V1 etc. Vn. So where Vi's don't satisfy any relations. So the symmetric product is going to be again taking product with the symmetric product. So that means we can just assume all the variables to commute, okay. The symmetric product means again taking product of basis elements but we just assume all the variables commute. Okay. So these are all the two different products that we have seen now. So now we are going to see another product, okay. So in which whenever some variable repeats, so we just want that product to be 0, okay. So that is where the exterior products comes in. So what is exterior product? So this is in some sense the way you want to think. So you want to think that it is just taking the product of Vi1 etc. Vik, but if some variable repeats, then we want to think that as 0. We want to take the product as 0. Okay. So this is what the exterior product gives us. So we don't want V times V. So V square should be 0. Okay. So of course all these products actually are different. So that is why we can use different notations. For the tensor products we use the tensor Vi1 tensor etc. Vik. For the symmetric product we can just simply write it as Vi1 times etc. Vik. For the exterior product we use Vi1 wedge etc. wedge Vik. So sometimes this is also called wedge product. Okay. So how one can actually construct this using algebraic ideas. So let us start with this two-sided ideal. Let's call it J. So you take this two-sided ideal, generated by. So now what we want just to declare that whenever two variable repeats, that should be 0. So then you can easily see that simply you can just take the two-side ideal which is generated by V tensor V, where V actually runs over capital V. If we take this ideal and then if we go modulo this ideal in T of V, then we get what is the exterior algebra. Okay. So again we start with V being just a vector space. So this construction valid for any vector space over complex numbers. Okay. One can do all these things in much more generality over general ring, commutative ring and so on. So we don't require it in that generality. we just focus on only the vector space level. So, we have this this natural algebra. So, you can actually see that this same ideal using this simple technique playing with the bilinearity of the tensor product, the same ideal is indeed generated by V tensor W plus W tensor V for all V W in capital V. Okay. So, this is, I will leave it as exercise. This is two sided ideal, generated by this V tensor W plus W tensor V. So, the way you observe this, for example, if you just calculate V plus W tensor V plus W, then it is exactly equal to V tensor V plus V tensor W plus W tensor V plus W tensor W. Now, suppose V tensor V is 0, that means all these things becomes 0. So, that means this is also 0, and if this is 0, if and only if all these things will be 0, because we can take W to be V. So, using this identity, one can observe that these two ideals are same. So, there is no difficulty, but it is easy to see that this is again graded elements. Okay. So, J is indeed a graded ideal. So, this is again indeed graded ideal. So, that means the algebra that we are going to get is graded algebra. Okay. So, now you can look at this natural quotient map from T of V to lambda of V. So, let us call it pi. Okay. So, this natural map again, if you take the image of T k of V, so that is if you denote it by T lambda k of V. So, this will be the kth graded piece or graded space. Okay. So, now this lambda k of V is what is called kth exterior product. Okay. So, this is indeed called kth exterior product. So, under this map one can actually denote general this W 1 etc. W k to be the image of this, we can just denote it by the wedge product. So, this is just a notation. So, what is important about this product is that whenever some variable repeats in this product, okay, then we just take it to be 0. Okay. So, with that observation, one can easily see that all the images of basis elements coming from T k of V, that is going to actually give you spanning set for lambda k of V. But since no two basis elements of capital V in the word that comes from this basis of T k of V should not repeat. So, that is going to give us this smaller spanning set. So, this is spanned by, so it is not that difficult to verify. So, you take all possible V I 1 wedge etc. wedge V I k. Now, this I 1 etc. I k should not repeat. Okay. So, this I 1 and I 2 and so on I k, all of them should be distinct. You can easily see that this relation actually tells whenever you switch V and W in the simple tensors, all you are paying is minus. Okay. So, V W, the wedge W is same as W wedge V. So, using that relation V wedge W equal to minus W wedge V. So, using this relation you can see that you can arrange these tensors in the increasing order. So, all I 1 etc. I k must be distinct and you can arrange them in the increasing order to get the minimal spanning set. So, that is the only condition that we are going to impose. So, this I 1 etc. I 2 are increasing and they comes from 1 to n. and that will form a spanning set for lambda k of v, and this natural minimal spanning set is going to be a basis. Okay. So, this is indeed a basis for lambda k of v. So, now it is not very hard to see lambda k of v is 0 for all k greater than n, because if you have more than n plus 1 elements, then you can see that if you pick this I 1 etcetera I k from that n plus 1, at least one of them should repeat. Okay. So, that means the product will become 0. So, there is no non-trivial element inside lambda k of v that spans. So, and it is not hard to see lambda 0 of v will be just the complex number, lambda 1 of v will be just your capital V, and lambda n v again. So, it will be spanned by this nth exterior product. So, you have to choose k to be n, and if you are choosing n distinct elements from 1 to n, there is only one choice. So, this has to be just V 1 wedge etcetera V n. Okay. So, this must be this one dimensional space spanned by V 1 wedge etcetera V n. So, and now since this is the basis of this lambda k of v, so it is easy to see that the dimension of this lambda k of v is just a binomial coefficient, which is n choose k, because you are choosing k distinct elements from given 1 to n. So, that is why it is a binomial coefficient. Okay. So, now if we start with a G module, let us say V is a G module. So, then it is not hard to see the relation that we are going modulo. So, that is indeed a G invariant relation. Okay. So, this is the ideal J is G invariant. So, J is G invariant. So, why? Because if you apply x v dot tensor v, then this is going to give us x v tensor v plus v tensor x v. So, now you can actually just add and subtract x v and x v. So, it is actually easy to verify for the other relations, maybe I will do that. You take this v tensor w plus w tensor v, then it is easy. So, let us do that. Take x acting on v tensor w, then we know that this is x v tensor w plus v tensor x w. So, now if you take x acting on v tensor w plus w tensor v, then we get x v tensor w plus v tensor x w plus x w tensor v plus w tensor x v. So, now you can see that you can group these two elements, and then you can group these two elements. Okay. So, then this is again inside J. So, this tells us that the ideal which is which is J generated by this v tensor w plus w tensor v, that is invariant under G action. So, that makes that the quotient space again. So, that implies that the quotient space is again a G module. So, that means this exterior algebra is a G module. Okay. So, now if we take this particular lambda k of v, you can easily see that this is indeed a G submodule. So, that is because if you take, you can just apply it on the basis element and then see what you are getting. So, the action is induced from the tensor product. So, the how this x is acting on the wedge, let us see. So, if you take x acting on this wedge v I 1 etcetera v I k. So, this has to be just a sum of the, it has to act as a derivation. So, it has to be sum of this x v I 1 wedge etcetera wedge v I k, okay, plus etcetera plus v I 1 vi1 which etc which x vik. Okay, so this is now using the property of skew symmetrization, you can actually rewrite in terms of the elements of this kth wedge products. Actually, one can just use the linearity, no issue. Like, so you can see that this xvi and vi1 is going to be linear combination of some vj's, okay, because this is an element of G. So whatever it is, so this is going to be just some summation kj vj. Now, if you take this wedge product, it will commute with the summation. So you can see that this is going to be again some linear combination of k wedge product. Okay, so that means this is inside this wedge kv. So this makes actually this lambda kv as also G submodule. So that means this lambda v being direct sum of lambda kv, okay, where k ranging from 0 to n, this is indeed G module decomposition. Okay. So indeed, actually we have given V module G, we have created like lots of new examples from that. If we start with G module V, then we have the tensors, we have the symmetric tensors, and we have this exteriors, okay, which is isomorphic to Sk of V, and then we also have this lambda k of V. So we want to see now, like, is there any natural submodule of Tk of V which is again isomorphic to this lambda k of V. Okay. So that is what actually gives what is called alternating tensors. Okay. So the correct things to replace here is the alternating tensors, alternating tensors. So which is analogous to this symmetric tensors. Okay, this is the symmetric tensors. So let us see the definition. Again, we can use the natural Sk action on the Tk of V. So recall that Sk acts on Tk of V by just permuting the tensor components. Okay, by permuting the tensor components. So that actually gives this natural Sk action. So now what we can do, we can actually define this alternating space. Okay. So this is the just you collect all the vectors that comes from Tk of V. When you apply the action of sigma on W, so now what we expect, we do not want it to be invariant, we want some sign to pop up. Okay. See, you look at the relation that we con modulo to get the exterior algebra. So whenever you switch x, V and W, so whenever you switch V and W, we are getting the minus. Okay. This V wedge W is same as minus W edge V. So that means whenever I switch the tensor components, then we want to get the minus side. So now if you take any permutation and then if you apply the permutation, you can easily see that any permutation can be written as product of what is called the simple transpositions, like product of transposition, which is Ij. So whenever you switch I and jth position of the tensor product, you are going to get one minus side. So if you use any permutation and then do this, then you are going to get the sign of that permutation. Okay. So that is what you demand here in the tensor. You take those vectors coming from this Tk of V, such that when you apply sigma on W, then you expect that you get the sign of sigma. Okay. This is the sign of sigma, and then that has coefficient for this. So now you can easily see that if sigma is actually a non-trivial transposition which actually flips I and j, so then this sigma W becomes minus W. Okay. So, that is why you need to have what is called this anti-symmetrization to get this alternating tensors. So, let us actually write down that map very explicitly. So, as before, we also have this natural quotient map from T of V to this wedge V. So, now we can take this natural quotient map and then restrict to this alternating tensor. Okay. So, this is going to be a map from the alternating tensor to naturally to this kth wedge product, because one can actually see that the kth wedge product is the image of the Tk of V. Okay. So, and by definition the alt Kv sits inside Tk of V. Okay. So, this is the kth wedge product. So, there is this natural map. So, indeed what one can prove it, this is indeed vector space isomorphism. So, this is indeed vector space isomorphism. Okay. The inverse map is given by what is called anti-symmetrization or the skew symmetrization. So, the inverse map, so let us write the inverse map to be some phi. So, this is the skew symmetrization or anti-symmetrization. So, this is a map from lambda kV to this alt kV, which is an element inside TKF, which is sits inside TKF. So, what is this map? You take any wedge product W1 wedge etc., wedge WK. So, which will be some basic element inside lambda K of V. Okay. So, it is enough to define it on this and then extend linearly. Okay. For example, you can do it on the basis. So, now if you take this W1 etc., wedge etc., WK. So, what you do, you just send it to the summation. Now, only we are doing this anti-symmetrization, we can just take the sign of this sigma and then we just apply it here, W sigma 1 etc., W sigma k, where sigma runs over Sk. Okay. It is easy to check this element is indeed an element inside alt k of V, and if you start with the basis of lambda k V, which is the natural basis that we have already given. So, V I 1 wedge etc., wedge V I k. So, where I 1 is strictly less than I k and then comes from between 1 to n. If we take this and then take its image to be that T I 1 etc., T I k. So, which is let us say phi of V I 1 wedge etc., V I k. So, these elements will form a natural basis. Okay. So, these elements form a natural basis for alt kV. So, this is what called skew symmetrization, and then using that one can actually get basis of this alt kV. Okay. So, now it is not that hard to see that this alt kV is a G module if V is a G module. Okay. So, observe that if V is a G module, then alt kV is also a G module. So, why that is true? Because the action of G commutes with the action of Sk, and this is actually the alt kV is defined using the action of Sk. Now, from this equation you can see that. So, if I take some element W in alt kV and then x in G and then let us say sigma in Sk, then what we get is, so we want to prove that x W must be inside alt kV. Let us apply sigma on x W. Since the action of sigma and x commutes, so this is going to be x sigma W, but x sigma W must be the sine of sigma times W. So, this is going to be giving us sine of sigma x W. So, from this equation you can see that x W is again element of alt kV. So, that means alt kV is a G module. Okay. So, now if we go back to that map phi that we have, or this natural restriction of the quotient map. So, this map will be again G module isomorphism. Okay. So, I will leave it to you to check. So, the natural G module structure on T of V and lambda V makes actually this pi G module map, because this pi is a G module map. Once you restrict to this respective submodules, again it will be a G module map, and since it is already a vector space isomorphism, so this becomes actually G module isomorphism. So, indeed we have this new representations coming from the alternating tensors or the wedge products. Okay. So, indeed it is really a very hard problem to actually construct, or construction is easy to understand. For example, like what happens when we actually use all these like basically they are functors, okay, on given G modules. Okay. There are these new things that we have learned. Okay. One is taking the tensors and taking the symmetric tensors, or what is called the sim. Okay. So, there is something called sim, and we also have what is called alt. Okay. So, basically given V module, one will be able to associate T k of V, sim k of V, and this alt k of V. Okay. So, here is the natural question. Suppose if we know some information about V, for example, let us say V is just a irreducible module, then what are all the information that one can actually expect on these modules? And you can see that even in SL2 theory, these questions actually becomes much more harder. For example, what we can do, we can actually take all possible like permutation combination and then keep applying things. Okay. For example, one can take sim power 3 and then alt power 4 on some representation V, and similarly one can take the dual sim power k and then alt power L, and then we can again apply sim power some L dash on some V, and then we can take the dual and so on. Okay. So, we can actually do all kind of different things, and then we can apply it on given using the given module. Okay. We have from the given module we have V dual, and then the tensors, corresponding tensors, and the home and so on. So, so many modules that we have already introduced. So, using them we can actually create lots of examples like this, but there are some basic questions that one can ask which will be not easy to actually answer. So, for example, like if we start with V being just V of m, okay, now we can just simply ask, so what will be the sim k of V of m? Okay. So, what is, we already know that the module is completely reducible. Okay. So, I will leave it to you to think about it, like can we actually write down explicitly the irreducible decomposition of this sim k of V of m. Okay. So, it is not that easy. Okay. So, I will leave some important exercise. So, if we take for example, V tensor V, then you can actually define the sim 2 of V and then alt 2 of V. Then one can prove that this V tensor V is indeed a direct sum of these two spaces. Okay. And we will see later that what this means indeed in terms of matrices and so on. So, basically it is writing that given matrix as symmetric matrix plus Q symmetric matrix. Okay. So, if V is a G module, then one can prove that this is indeed G module decomposition. G module decomposition. Okay, I will leave it to you to check this. Okay, I will stop here and then I will continue with some other constructions of representations in the next class. So, mainly we want to actually understand these bilinear forms on bilinear forms that can be defined on the Lie algebra and using some again representations of Lie algebras. Okay, so we will talk about it in the next class. Thank you. I will stop here.